find center of mass. The first type we focus on is type 1, which is just looking at point masses in the discrete case. And our goal will be to find the center of mass of the system. Let's say I have two masses, M1 and M2, and I want to find where the center of mass is. So if I want to balance this, should I put my fulcrum or ballast point in the middle? Should I put it to the left, to the right? Well, as you may have already guessed, it depends on how big the masses are. Which is this one heavier or is that one heavier? So we're just going to leave them in variable terms as M1 and M2, and we're going to say, I don't know, somewhere here, let's say, we're going to call that our fulcrum where the thing balances, and we'll say X bar is where we're going to position the fulcrum to balance it, and we'll call this location X1 and this location X2. For the system to balance, we must have M1 D1 equals M2 D2, and we can find that distance. It'll be a signed distance depending on where my balance point is. So if my balance point is to the right of this X1, then D1 will just be right minus left, X bar minus X1, and D2 will be X2 minus X bar. So now I want to find X bar, so I'm going to go ahead and do the algebra. I'm going to go ahead and distribute the M1s, and then I'm going to move this X bar business to the left, this business to the right, so I can isolate my X bar. So all the X bars are on the left, the rest are on the right. Now I'm going to factor out an X bar. We are almost there. We have X bar, so I'm going to divide both sides by the total mass of the system. So now I have the location of my X bar determined in terms of where my M1 and M2 were placed and how big my M1 and M2 were. These guys are called moments, and this guy, of course, is the total mass of the system. So I have the sum of the moments, which are just the signed distance from an axis, depending on where the axis is. We'll look at an example and see what that means, times the mass of whichever item you're looking at. So if we extend this to more items, not just two masses, we will end up with the sum of all the mixi in the numerator divided by the sum of all the masses in the denominator. So I don't necessarily have to have just two, I could have many masses. Let's look at an example quickly in this one dimension that we're dealing with, only with x's and nothing else. So there's two masses, one of them is 2 kilograms, another 1 kilogram. They're 1 meter apart. Where should we place the balance point to find the center of mass of the system? So think of it like a seesaw, 2 kilograms on this side, 1 kilogram here, and like a seesaw, something that tries to connect them together. Of course, we're going to assume that that mass is negligible. And we're trying to find the balance point for the system. Well, this is 2 kilograms, that's 1 kilogram. If I try to put the fulcrum, let's say, right in the middle, you might have already guessed that if this is heavier, this is going to tip down and it's not going to be the balance point. And again, if I put it somewhere here, let's say, again, not only is this heavier, it has this additional length also contributing to it, so it's going to tip this way again. So intuitively, you might think it has to be closer to the 2 kilogram mass, but we'll go ahead and find that out with information given. So we're going to say, I'm going to let my 0th place be right here. It doesn't matter where you let it be, you can call that 1 if you want. And if this is 1 meter apart, then I'm going to call this to be 1. So I'll call my x1 0, I'll call my x2 1 meter away from it. And then my M1 is 2 kilograms, and my M2 is 1 kilogram. So if I want to find the balance point, I have my M1 x1 plus M2 x2 over the total mass of the system. So I just plug them in, mass 1, 2 kilograms. X1, based on what I call this to be the 0th location, is 0. M2 is 1 kilogram, X2 is 1 meter away. all over the total mass 2 plus 1. And if I compute that, I'm going to end up with 1/3. So basically it says that between 0 and 1, I have to place my fulcrum somewhere right there if I want the system to balance. So closer to the 2 kilograms as we had suspected. Now I chose to call this 0. I didn't have to. I could have called it 1, and I could have then accordingly called this 2 and computed to see what happens. I should still get that I should be 1/3 away from the 2 kilogram object and 2/3 of the way from the 1 kilogram object. Let's go quickly look at that. So notice now I just said, well, my 0th location is back here. I'm going to call my x1 at 1, and my x2, if it's 1 meter away from it, that's got to be 2. Let's go see what will happen. M1 is 2, x1 is 1 in this case. M2 is 1, x2 is 2 in this case, because it's actually 2 units away from here, only 1 unit away from here, all over the total mass, and this ends up being 2 plus 2, which is 4, over that, which is 4/3. It simply gives me that based on the axis I set here, my center of the system will be at 4/3, which is really, notice, 1 and 1/3. So nothing changed. My fulcrum got placed at 1 and 1/3. Still 1/3 of the way from this guy and 2/3 of the way from that guy. So it doesn't matter where I position my 0, it just makes it easier to put a 0 for me there. So we can generalize the idea we just talked about and extend to 2D dimensions where my masses are placed somewhere along the x and y axis. Not actually x and y axis necessarily, but somewhere along in a 2 by 2 dimensional system. Let's say I put my M1 there and I put my M2 there. So if the location of M1 is at the coordinates x1, y1, M1 will be y1 units above the x-axis and x1 units to the right, in this case, of the y-axis. And similarly, if M2 is located as at x2, y2, then I have this distance that it is away from the x-axis and this distance that it is away from the y-axis. So in this case, that creates 2 moments. Moments about the y-axis and moments about the x-axis. The tendency of this system to swing about the y-axis and lose its balance, and the tendency of the system to swing about the x-axis. So we look at 2 moments. So the tendency of the system to rotate about the y-axis depends on how far this guy is from the y-axis. So notice my M1 is x1 units from the y-axis. Same thing for M2. How far is M2 from the y-axis? M2 is a distance of x1 away from the y-axis. So what I really end up with is M1 x1 plus M2 x2 plus ... if there are more items, Mn xn. So the moment about the y-axis is really the sum of mi xi. I'm not going to put from I equals 1 to n. It's implied that I'm summing up n items. So mi xi is the moment about the y-axis. Similarly, the moment about the x-axis, or the tendency to rotate about the x-axis, really depends on how far this guy is from the x-axis. And notice how far this guy is from the x-axis is a distance of y. How far is M2 from the x-axis? It's the tendency to lose balance and rotate about the x-axis. That guy is really y2 away from the x-axis. So we end up with M1 y1 plus M2 y2 plus, if you have more items, Mn yn, and similarly the sum mi yi. So we got the moment about the y-axis, and we got the moment about the x-axis. Now notice from above what the balance point analysis led us to. The balance point was the sum of the moments over the sum of all the masses of the system. So sum of the moments over the total mass of the system. We apply that here in both cases, and we're going to get our x sub bar and y sub bar. So just like from above, again, I have the sum of the moments divided by the total mass. I'm going to do the same for the x's and the y so that I can get my ordered pair for the center of mass of this system. So x bar is the sum of mixi, which in this case, notice that's actually the moment about the y-axis. So I have m sub y over that, and I have y bar. In this case, we have m sub x over the sum of the mass of the system. So we have our, which are comparable, x bar and y bar. The same. Notice, don't confuse this. X bar has the moment in y above it, and y sub bar has the moment in x above it. So let's look at an example. Here we have a system that has 4 masses, and each of the masses are located at these locations on your coordinate system. We're going to go find m sub x, m sub y, the moments, and then also find the center of mass for this system. So again, we call the moment about the y-axis is really the mass times the distance from the y-axis, which is really the x-coordinate of each of the points. So we open up our sum, take the product of the x-coordinates, the signed distance, and the mass, and we get 42 for the moment about the y-axis. For the moment about the x-axis, again, it's the mass and its tendency to rotate about the x-axis, so it is 1 units away from it. We open up our sum and plug in accordingly. Put in the masses and the y-coordinates, and we end up with -3. We also have to go find actually the center of mass of the system. So we have to find x bar and y bar. So we got the moment about the y-axis over, I have to find the total mass of the system. And then I have -3 over, and the total mass of the system looks like it's going to be 11, 12, 16 when I add them up. So make a side note of the whole mass of the system so that you can find it when you're finding the center of mass. So we end up with the location where this system is going to balance is going to be at 21 over 8, it looks like, and -3 over 16. So that is the discrete case where you have point masses located at certain places. You're going to find the moments, and then you're going to find the center of mass based on those moments. The continuous case where we have actually a flat plate depends on the derivation of it, sort of depends on this idea, and we're going to look at that next.